Welcome to this video in our animation series about the differential pressure control valves, DPCVs. In this episode, we'll take a closer look at one specific DPCV of the IMI Climate control range, the compact DP. We'll explore how it functions and how it differs from other DPCVs. This valve operates a bit differently because with the compact DP, you set the flow rate rather than the differential pressure, DP. Actually, in reality, you set the flow rate linked to the balanced DP. But how does that work exactly? As explained in earlier videos in this series, the working principle of a DPCV is essentially a balance of pressures and therefore forces. The same applies here. This is a high pressure P1 and the low pressure P2 is communicated via the capillary to the bottom of the compact DP. When P1 increases, or more precisely, when the difference between P1 and P2 increases, this will make the dynamic element in the DPCV to close. When the difference between P1 and P2 decreases, the dynamic element will open again. This balance is influenced by a spring that maintains a constant differential pressure. Importantly, the spring force is not adjustable, which means the regulated dP remains relatively constant. We could see the compact DP as a differential pressure controller and a control valve in series. The differential pressure controller keeping a constant dP over control valve and coil. It is the job of the balancing and control plug to take out the difference between the stabilized differential pressure, 15 kPa, and the pressure drop of the coil, thus balancing the circuit to design flow. Now, how do we control the flow rate? By adjusting the setting wheel, we alter the pressure drop across the balancing and control plug. This pressure drop, combined with the delta P of the coil, determines the resulting flow. However, this also means if the assumed coil delta P is incorrect, the resulting flow will be inaccurate. Let's illustrate this with two examples using the sizing chart for a compact DP DN50. In the first example, we select a flow of 250 liters per hour at a coil DP of 10 kPa. By crossing these two values on the chart, we find the corresponding presetting. This setting creates a pressure drop across the valve that, combined with the coil DP, gives the balanced DP, for example 15 kPa. In the second example, we choose a lower flow rate of 200 liters per hour and a coil DP of 12 kPa. By checking the chart again, we find the same presetting value. So the total differential pressure remains the same, 15 kPa, but the split between the valve and the coil pressure drop has changed. In the first case, the control plug takes 5 kPa and the coil takes 10 kPa. In the second case, the control plug takes 3 kPa and the coil takes 12 kPa. Let's run a simulation high select to see what happens when the coil dP is incorrect, perhaps due to incorrect selection, system changes, or fouling. Assuming the compact dP maintains a stable delta P of 15 kPa, we can calculate the kV values in series. One for the coil, 10 kPa and 250 liters per hour. One for the control plug, 5 kPa and 250 liters per hour. We see a total kV of 0.6455. Let's fill that in the calculation. We see a correct flow rate of 250 liters per hour. But imagine that the actual coil dP drops to 5 kPa instead of 10 at the same flow. This means the total kV increases to 0.7905, which will cause the total flow rate to rise beyond what was intended. This clearly demonstrates that the compact DP is indeed a true differential pressure control valve but that accurate flow control depends on the actual pressure drop across the coil. For simplification reasons, we did not talk about the proportional band of a DPCV, or a differential pressure controller. Check out other videos in this series to learn more about DPCVs and proportional band.